Hello, this presentation will cover how everything we've talked about in R2 applies to R3. So we're going to talk about representing points, how to represent linear and affine transformations, homogeneous coordinates, and matrix representations in R3. We've covered all these topics in R2. The principles are extremely similar in R3, so we'll go pretty quickly to just talk about how things are different. So let's get started. So first of all, points, or vectors, in R3 are triples. So we'll use a notation like x vector still has components x1, x2, x3, and that's a shorthand notation for the column vector x1, x2, x3. Or sometimes we'll call it xyz, where now xyz are scalar values, and that's the column vector xyz. So the usual representation of points in R3. However, what's different, the axes, the xyz axes, are in a different orientation than expected, than is usual. So we're already familiar with xyz axes from, say, calculus, but the axes here point in different directions. So in computer graphics, the convention is that the x-axis points rightward, the y-axis points upward, and the z-axis points forward out of the surface that we're writing on. So it's the x-axis is pointing that way with the way my arm is pointing, the y-axis is pointing upward, the z-axis is pointing straight out of the blackboard towards you as the viewer. And so it's a perfectly good coordinate system, but it's not the one you're used to. It takes a little bit of getting used to when you start doing computer graphics. So in calculus, we have x forward and y sideways and z up, and it makes sense there because we're talking about functions of x and y, and so it makes sense to have them flat and look at the height of the function, height of the surface as the valued function. But in graphics, we're sort of thinking of drawing on a screen, and in 2D graphics, it makes a lot of sense to have x pointing this way and y pointing upward, and then we add on the z-axis pointing outward. Okay, so we have to get used to this convention. It definitely takes a little bit of getting used to. But one thing that is good about this is it's still a right-handed coordinate system. So what I mean by this is that cross products and so on we can still visualize using the right-hand rule. So cross products still use the right-hand rule. So for the right-hand rule, right, remember, say we take let's look at the standard vectors. I is 1, 0, 0, j is 0, 1, 0, and k is 0, 0, 1. So these are the standard basis vectors. And if we take something like I cross j, this is the usual vector cross product, that's equal to k. And the picture with the right-hand rule, if you remember how this works, is, you should, is you take the I vector, which is pointing along the x-axis, and you push it flat with your fingers up towards the j vector, because it's I cross j. Your thumb will be pointing in the direction of the product, the cross product, the k vector in this case. So we're still using the right-hand rule here. It's just like a rotated version of the standard coordinate system, so that now x points to the left, y points upwards, and I'm sorry, x points to your right, y points upward, and z points out. So next we want to talk about the definitions of things like transformations, and linear transformations, and affine transformations, and of course translations. And these are actually all word for word the same as the definitions that we did for R2. So the definitions of these things in R3 are identical to the definitions we used for R2. Definitions, I should say, in R3 are identical to the definitions in R2. I mean, just exactly identical, word for word. You can read it off, but you just have to interpret points as being 3 tuples instead of 2 tuples. So, for instance, a linear transformation is still a mapping that the transformation of a sum is the sum of the transformation of the summons. The transformation of alpha times x is alpha times the transformation of x. Those two properties still define linear transformation. A translation still has the form t sub u when applied to x is equal to x plus u. So this is a translation still. Now u, of course, is in R3. It's u1, u2, u3, say. So it's in R3, not in R2. But a translation still just moves things around, changes their position without changing size or shape or orientation. An affine transformation still has the form a of x equals b of x plus u, where b is linear. And so the definitions are just word for word the same. So to give a couple examples, we can mention some scaling transformations. I'll use 2 notations for this. The first one is uniform scaling. Uniformly scaling something means to just multiply by a fixed size. So I'll use S alpha of x is equal to alpha times x. That just scales everything by the factor alpha. So if alpha is 2, we would double the size of everything, keeping the origin at a fixed position and sort of doubling everything in size around the origin. And or the non-uniform scaling in general, we have scaling S sub alpha beta gamma with alpha beta gamma scalar values. This applied to x1, x2, x3 is equal to alpha x1 beta x2 gamma x3. So again, alpha, beta, and gamma are scalars. They're real numbers. So these are 2 types of scaling, very similar to the previous scaling we used, except that now there's 3 axes to scale along instead of 2. Now, however, rotations are more complicated. So our notation for rotations, well, just remember for R2 we had 2 types of rotations. We had rotations around the origin, r sub theta we call them, and we had generalized rotations that held some other point fixed, u, and call it r superscript u sub theta. So for this presentation, I'm only going to talk about things that rotate around the origin, but the thing in R3 is we have more freedom for the direction of rotation. So what happens here is we use the notation r theta subscript u, completely different than the old notation that superscript u here. This is going to rotate angle theta around axis u, and u had better be non-zero, so u is not equal to 0, and with direction given by the right-hand rule. So this needs some explanation, and we'll do an explanation in an example here. We've got this vector u sitting in space. We think of it's fixed at the origin. So a vector is going from 0 to u. We think of holding the axis containing this vector fixed. So here's the line. It's not necessarily one of the standard axes. We take the line holding that vector u, and we're going to rotate everything around that line. We're going to spin the whole of R3 around that line, holding the line fixed. And the direction of spin is given by the right-hand rule. I grab onto the u vector with my right hand, thumb pointing in the direction of the positive direction of the u vector, the direction of the u vector. The curl of my fingers tells me the rotation direction if I'm using my right hand. So the direction is given by the right-hand rule. So let's do an example of this. And we'll do more examples in later classes. Let's consider r pi over 2I, which is rotating around the x-axis 90 degrees, or pi over 2 radians. And I don't mind if you use radians or degrees. You can also call it, so it's also known as, aka also known as r 90 degrees I. That means the same thing as far as I'm concerned as r pi over 2. So what does this transformation do? So how does r pi over 2I act on the standard basis vectors I, j, and k? Okay, so let's think about this. It's not that hard to visualize because it's a very simple rotation. Here's my x-axis. Here's the y-axis. Here's the z-axis. The I vector is pointing, I is pointing along the x-axis, j is pointing along the y-axis, k is pointing along the z-axis. And we're going to hold the x-axis fixed and spin everything around the x-axis through 90 degrees, direction given by the right-hand rule, so it's going to be spinning this a ways. So it's going to, so we will map I, will get mapped to itself. So r pi over 2I, it's going to send I to itself because we're holding the x-axis fixed and spinning things around it. So the I vector is on the x-axis, so it doesn't move at all. J, I claim that's going to map to k. So the point here is that I'm looking, let me use the right-hand rule from this side. I grab onto the x-axis, so I'm looking straight on with my right hand at the x-axis, and I'm looking at the curl of my fingers, and so they're curling this way, so everything is going this way. So the j vector is pointing up like my forearm. When we rotate it 90 degrees, think of my upper arm as the x-axis, we rotate it 90 degrees, it's pointing in the positive z-axis direction, that is in the direction of k. So r pi over 2I maps j to k. And what does it map k to? Well, the k-axis is pointing out of the blackboard towards you guys viewing the video. The x-axis, the I vector, is along my forearm. I rotate 90 degrees, direction given by the right-hand rule, and so we end up on the negative y-axis. So k maps to negative j. Let me write that a little more clearly. So this is how rotations work. More generally, you can rotate around u, and it gets harder and harder to visualize rotations in R3 as you let u vary, but we'll start with this as the first example. So now we want to talk about matrix representations of linear transformations. And we'll use 3 by 3 matrices in R3. So matrix transformation linear. So here, let's just do a couple examples first, and the general principle should be pretty clear. Basically, it's the same rule as in R2. The columns of the 3 by 3 matrix give the images of the transformation on the standard basis vectors. But let's do an example first. S sub alpha, beta, gamma is represented by alpha 0, 0, 0, beta 0, 0, 0, gamma. In other words, the diagonal matrix with entries on the diagonal alpha, beta, gamma, because it's easy to check that S, alpha, beta, gamma applied to a column vector x, y, z is equal to alpha x, beta y, gamma z. In other words, we've just multiplied the x component by alpha, the y component by beta, and the z component by gamma. And that's clearly what happens when you take this diagonal matrix and multiply it by the column vector x, y, z. So another example here, more complicated one, and this is even different than the one on the previous board. Let's try rotating 90 degrees around the axis, the z-axis, or the k-vector. What matrix represents this? So let me draw a picture over here to the side. Here's the x-axis, here's the y-axis, here's the z-axis. We're rotating around the vector k, which is the standard unit vector along the z-axis pointing out of the blackboard. What's the image of x when we rotate around the vector k? Well, I take my right hand and grab onto the vector k with my thumb pointing out of the head of k, and then x, we're rotating 90 degrees, so the direction goes this way. So the x-axis, or the I vector, goes up to the y-axis, or the j vector. So the image of the x-axis, the image of the I vector is 0, 1, 0. And that's actually the first column of the matrix representing our pi over 2k. The j vector on the y-axis rotates 90 degrees down to the negative x-axis. So it goes, the unit vector 0, 1, 0 gets mapped to minus 1, 0, 0. That's the image of the j vector. The k vector is fixed. We're rotating around the axis containing the k vector, so it doesn't move. So it's just 0, 0, 1. And it's not hard to check that this matrix I wrote out corresponds to this picture. More generally, if A is linear, a linear transformation, we let U equal A of the I vector, V equal A of the j vector, W equal A of the k vector, and then A is represented by the 3 by 3 matrix M, which is in block form, it's U, V, W. Or if we write it out fully in component form, if U is U1, U2, U3, the first column is U1, U2, U3. The second column is the column vector of V, and the third column is the column vector of W. So similarly to what happened in R2, the linear transformation A is represented by the matrix M, a 3 by 3 matrix now because we're in 3 space, where the columns of the matrix are the images of the transformation on I, on J, and on K. So next we want to talk about homogeneous representations and 4 by 4 matrix representations. So homogeneous coordinates in R3 and 4 by 4 matrix representations of affine transformations. So first of all, let's talk about affine let's talk about homogeneous coordinates first. So if we take a 4-tuple, x, y, z, w, this is a homogeneous representation or homogeneous coordinates for a 3-tuple, a point in R3, namely of the point x over w, y over w, z over w. This is in R3, and we should assume here that w is not equal to 0. We will later on give some meaning to w equal to 0 as points at infinity, But for the moment, let's just talk about W not equal to 0, so ordinary finite points in R3. So this is the way we represent a 3-tuple as a member of R3 with 4 coordinates. Notice again, there's multiple homogeneous representations for the same point in R3, because if we multiply uniformly x, y, z, w by any non-zero scalar, we still represent the same point in R3. So now suppose that A is affine. So A of x equals B of x plus t, where B is a linear transformation and t is a vector in R3, so A is an affine transformation. And let's suppose also that suppose B has the 3 by 3 matrix representation as a linear map of the matrix M, which is, I'll write out the entries as M11, M21, M31, M12, M22, M32, M13, M23, M33. This is the matrix I described on the previous board as U, V, and W, but I'm now just writing out with little MIJs instead. And we'll suppose that we'll also suppose that T is the column vector T1, T2, T3. Then, if we let N be the following 4 by 4 matrix, then the 4 by 4 matrix N, you can write this in block notation as M 0 transpose T1, but to write this out more explicitly, we've got M11, M21, M31, 0. That's the first column of M with a 0 at the bottom. M12, M22, M32, 0. Second column of M with a 0 at the bottom. And M13, M23, M33, third column with a 0 at the bottom. Fix that typo there. And then the final column is T1, T2, T3, and a 1 at the bottom. Then this represents the affine transformation A. So it always works out like this for affine transformations. We've always got the 3 zeros here. So this is just showing that this, for the time being, we always have the 3 zeros, and we've usually got the 1 there just because it's an affine transformation. The 3 by 3 block here is the M part. This is the linear part of the affine transformation. And the column vector at the end is the translation part of the affine transformation. So this is very similar to what happened in R2, except now we've got a 3 by 3 part and a 3 vector, and the bottom row it has 3 zeros and then a 1. But other than that, this works out and represents A in the sense if you take any homogeneous representation of a point in R3, N times that representation gives you the homogeneous representation of the value of the transformation A of that point in R3. So exactly as before, the 4 by 4 matrix represents the transformation A. And that's all for this presentation. Thank you very much.